Hi, Dave Littman, Truth in IT. Welcome to today's webcast, Testing the Limits, Ensuring Performance in Ultra High-Speed Ethernet Networks. Today's webcast is sponsored by Keysight, and in just a second, I am going to be bringing out our panel. Today, we will be led by Charles Seifert. Charles is Senior Manager, Platform Hardware Product Management with Keysight. And Charles and I will be joined by Jeff Twombly, who is Vice President Business Development with the Credo Technology Group. And Jeff and Charles and I will be joined by Alan Weckel. Alan is co-founder and analyst with the 650 Group. We expect today's webcast to go probably about 45 minutes, and we'll be taking your questions and comments in the chat room. We have staff standing by from Keysight to answer any questions you might have about the content, and staff standing by from Truth in IT to answer any questions you might have about the video stream or the audio quality. So let's get right to it. Here's what we're going to cover today. We're going to talk about market drivers and growth trends with Alan Weckel. We're going to segue into business drivers and challenges, both from the challenges in the silicon itself to the challenges that the network operators are seeing. And then we'll have an open panel discussion and talk specifically about Keysight's Aries 1 M 800 gig E solution. So let's get right to it. We've got a lot to cover. Alan, let me hand things over to you. You know, network bandwidth requirements are growing at 30 to 40% year over year, and mega applications are really driving the need for more network bandwidth. If you would, give us a closer look at what your research is telling you about the market landscape.
Yeah, no, absolutely. And thanks everybody for attending. So if we look at the market, we've been growing, as you mentioned, 30 to 40% per year. But in some of these new growth markets, such as AI, as we think about the digital economy and all these IoT devices that are being driven by 5G and 6G is just around the corner, we're getting use cases that are actually growing north of 30 to 40% per year. And that's putting an additional demand onto data center networks out there. So if we go ahead and transition to the next slide here, what you'll see happening is that the hyperscalers are really becoming larger and larger every year. And they're putting a tremendous amount of bandwidth demand into their suppliers. And then also they're also driving certain applications out there. So if we think about moving to higher speeds, such as 800 gig, it's really going to be driven by the logos on the right of this chart. And that's a little bit different out there than what we've seen in the past. We have far larger server installed bases, and that's going to lead to more speeds and feeds. More ports, some more bandwidth, and then also we're going to begin to see a lot of customization out there. So as we kind of think about the market and 800 gig, it's really going to be driven by the largest customers starting right now in proof of concepts, and then moving to the broader market very soon out there, but in volumes that we just haven't seen in the past out there. So we're talking hundreds of thousands of ports from the get-go, ramping to millions in a matter of quarters. And that's something that we didn't see with 400 gig or even 100 gig, just these huge, massive volumes out there. If we kind of think about where CapEx is being spent these days on the next slide, about 2/3 of CapEx is being spent on compute and storage, kind of looking at the pie chart here on the left, and about 1/3 is being allocated to networking. If we think about the next 12 to 18 months out there, networking is going to increase as a percent of spend. This is being driven by the move towards 800 gig and also on these new AI workloads, which have additional networks to them. So a tremendous increase in the number of ports per server and the bandwidth per server out there. So we're kind of in a golden age there of networking where we have multiple pillars of growth, and the CapEx allocated to networking is going to increase out there. If we transition to the right side of this chart here, it just shows some of the larger hyperscalers out there really showing this change in time, where you can say that if we were on the left-hand side of the chart, Google was really the largest consumer of data center equipment and drove a lot of what we saw out there in speeds and feeds. If we go to the right-hand side, Amazon is now the largest, and we can expect them to be one of the first adopters of 800 gig technology, and again, in huge volumes out there. So a little bit of a transition when we think about who's driving the first 100,000 or first million port volumes out there. It's a little bit different this time around out there. And a subtlety in that is Amazon is infrastructure as a service, or say more enterprise focused. Whereas Google was more social media and search focused out there. So a little bit of a transition towards the enterprise market as an early adopter this time via the IaaS space. If we go ahead and transition to the next slide, now this kind of reinforces where we started the conversation on bandwidth. So bandwidth and data center switching is about to grow kind of more around 50% out there. What you see on the bottom there, kind of the traditional layer 2 networks is in that 30 to 40 that we started at. But these new use cases or workloads out there are driving a far higher bandwidth growth. We'll start with AI, definitely growing at north of 100% per year. Remember, AI is multiple networks, not just one, so significantly more ports and use cases out there. And then we kind of have a layer 3 and DCI networks also growing at a significantly higher CAGR out there. This is important because if we shift to the right-hand side of the chart and say, what does this mean? It means that these new pillars of growth are going to contribute more and more to the overall data center switch market. That means more ports, more higher speed ports, and a faster rate of adoption out there. And that's where we see Keysight and Credo kind of pushing these new products, and the key theme here of faster to market and quicker adoption there. We just need to move quicker as an industry. But implied on the right here is that AI is going to be a significant part of network bandwidth in just a few years relative to being tiny today. And that's one of those key and new pillars of growth in the 800 gig story. It's why the industry is so excited about it and why we expect record port shipments and record revenues out there. If we kind of transition to the next slide here, this has two separate sets of data on it that I think can help ground us in the numbers. The left-hand side is really looking at port speeds with time, and I've kind of aggregated a few technologies together here to make the chart easy to read. But you'll see we're at this pretty large inflection point here of 800 gig ramping this year and rapidly into next year. And you can kind of read between the lines that it will become the largest port speed in the data center by 2027, 2028 out there. So huge growth and a far quicker ramp than what we saw at 400 gig or 100 gig in the past. And then if we look at the right-hand side at the underlying technology there, you can see the industry is going to rapidly move to 112 gig SerDes. So if we think about 400 gig as the 56 gig SerDes generation, 112 gig is going to drive the 800 gig and 1.6T generation pretty quickly there. And it takes over as the biggest volume or biggest contributor in the market. So at an industry level, this is going to reflect on vendors very rapidly moving towards these higher speeds. And again, this theme of multiple parts of the network out there. It's not just one data center network like we've seen in the past. It's literally 6 or more networks when we think about the DCI network, the multiple networks allocated towards AI fabrics out there, and then your traditional server access. So there's a robust need to increase the speed of testing and then also increase kind of the capability of the connections out there. And that's going to be an exciting part. So with that, I'll transition to my final slide here. Let's just take a snippet of kind of where Credo plays here. If we look at the AEC market, this is a relatively new market that handles server access there. It's going to become the majority of server ports very rapidly here. Servers with DAC and traditional connectivity just can no longer meet the speeds and feed scale that's necessary out there. And AEC plays a pivotal role in that connectivity. And this is important when we think about the ecosystem as a large, right? These hyperscalers are going to move to these new technologies. They're going to require testing, and they're going to require these vendors to become key strategic partners in areas that weren't necessarily an area of emphasis in, call it the 100 gig upgrade cycle out there. So there's this huge opportunity there for vendors to insert themselves in these technologies. And as you can see on the chart here, this becomes an incredibly large TAM, where historically this was just a DAC cable for the last 20 years. So this theme of new markets and new growth opportunities becomes very apparent here. So those were just some highlights at a market level to help ground us on some of the numbers out there.
Okay, great, Alan, thank you. And, sort of keeping in line with the market landscape, thank you for giving us that overview from your perspective. And now we want to look at it a little bit from the perspective of the manufacturers of high-speed Ethernet network equipment. So Charles, talk to us a little bit about the business drivers and challenges that you guys are seeing.
Well, thank you very much, David, and great set of information from Alan. So very true from the perspective of Keysight and what we see around the globe. What really we really have multiple axes here, where we have pressures coming in to the manufacturers of equipment, starting all the way from the silicon to interconnects to the actual networking equipment itself and test systems for the equipment. And one of the more difficult, which affects the technology and affects the investments required by all of the players that are supplying into this market, as well as the customers that Alan mentioned, the very large customers. We have to now adopt these technologies in decreasing adoption timelines. So the schedule, if you will, has been shortened dramatically. So to give you some idea, to go from 10 gigabit to 100 gigabit Ethernet, which happened in the early 2000s, that took almost 10 years. You could even say it took 15 if you really count all of the transitions in between, but it's a very long time. And when we went from 100 gig to 400 gig, which you saw on Alan's chart, has already been implemented and deployed, that took about 5 years. Now that we're going from 400 gig to 800 gig, the adoption timeline now is somewhere between 2.5 to 4 years. And at the same time, even the standards groups that have to develop our standards so that everything interoperates correctly, even those timelines are cut in half. So this is what we call decreasing technology adoption timelines. The other aspect of this that Alan mentioned is, as we have to go faster, in other words, more bandwidth has to be added to the network in a shorter period of time. Unfortunately, the complexity of implementing Ethernet and similar related technologies to it have become very complicated. In 100 gig, there was a little bit of complication. The beginnings of something called forward error correction was introduced into Ethernet, but it was optional. Didn't really need it. You could move on without it. When we moved to 400 gig just a few years ago, forward error correction became very important, and something called PAM4 signaling became very important, dramatically, exponentially increasing the complexity of implementing the new technologies from the silicon level all the way to the network switch or router. And as we move from 400 to 800 gig, it's a very similar level of complexity, but yet again, it's running faster. So when we have things that are faster, there are impacts to what the equipment, the silicon can do, what the equipment can do as a result of what the silicon can do. So that complexity is increasing when we move from 400 gig to 800 gig. And then at the same time, The old 5 nines, as they used to say in telecom for reliability, that's out the window. We actually have to do far better than that. So what happens is from the silicon provider to the test equipment manufacturer, to the network equipment manufacturer, to the interconnect manufacturer, we all have to now produce equipment that far exceeds the tolerances that are in the IEEE or OIF standards, because the requirements in the real world do exceed the bare minimum requirements to make the technology work. So it's not just about making it work and make it work with everybody else. It's about make it work reliably and far better than the tolerances that are given to us by the standards body. So that is a very tough challenge, and it becomes somewhat subjective as to what the goals are. And we'll talk about what those goals are and the range of subjectivity later on. And then the last point is getting products and services to market faster at scale. Now, this is a big problem as well, because this involves investment, huge investments, and it involves investing in shorter periods of time. So we are now investing more R&D in a shorter period of time to accomplish something with a shorter schedule to get to the market with a higher degree of complexity and higher expectations of reliability. Put all that together, and this makes very complex projects and product development schedules for everyone involved, from the silicon manufacturer all the way to the final end user who buys the equipment and implements it. And at the same time, someone like a Google or an Amazon, they have to test all of this new equipment. It's flooding into them, and they have to change out their network infrastructure, which means they have tremendous challenges because we're talking about a large number of ports, and getting their services to the market faster to compete with the other providers out there. So this is why we have a circle here with arrows, because this is just increasing. And on the near horizon is the shift to 1.6 terabits. So we know that's coming. We're not as worried about it at the moment, but for deployment, but here we're focusing on 800 gig, and this is the next big deployment, which we're going to talk about. Jeff, do you have any comments you might want to make here from when you're experiencing?
I think Charles, you touched on it, perfectly. Again, I always go back to, we rode that 10 gigabit per second, kind of flat line for, 12 years and beyond. And then again, when the data center became the business and we started just seeing the cloud infrastructure really develop, getting on that curve of going single lane rate, 10, going to 25 gigabits per second, 50 gigabits per second, now at 100 as the mainstream deployment. And again, we're looking beyond to that to 200. It just says we have to not only climb that ladder faster, but we have to do it in an ecosystem way that we can get to that scale, as you mentioned in the bottom left here. And to me, that's what it's really all about. We can do one-off demonstrations in the lab. We can do certain rack scale, but until you can get to that scale where you can actually deploy, economically from an energy efficiency perspective and from an overall cost of ownership, it just won't deploy. And we need to make that happen because the demand of those workloads are here upon us today.
Absolutely.
Okay, great. Thanks very much, Charles and Jeff. And Jeff, Charles touched on the aspects of the silicon itself and the aspects of it that both facilitate the development of high-speed Ethernet networks, but also some of the core issues that still need to be overcome in this space. So maybe you could talk about that for a bit, and then we'll get more into the network operator's perspective.
Yeah, absolutely. And again, thanks, to Alan for a great tee up, and then Charles for that good summary, because I think it puts things in perspective, for this slide, being the silicon guy in the room, obviously it kind of starts at, we got to be able to, move signals, at that raw level, at the board level, at the wire level, at the optics level. So if I look at this slide, I can talk about the high-speed SerDes, and I'll dive into that. I'll talk about the cost and power reduction challenges, and cooling is an integral part of that. But to me, I can simplify the slide into PPP. It's, you got to be able to deliver the performance that meets the application requirement and with a lot of margin, as Charles pointed out, 5 nines is out the window. You got to be at a power or an energy efficiency ratio that allows for these deployments, because we're not talking, we're talking new infrastructure as well as brownfield infrastructure. And then you got to do it at an economic point. So I think it's important to go back. If we looked at the transition from 25 gig SerDes, single lane rate, to 50 gig SerDes lane rate. Again, PAM4 got introduced. There was a, if I look at that on scale, we were ready as an industry from a technology evaluation and deployment level back in 2016, 2017. Right. But it really took to 2019 and really 20 to get to a point where we are today, where we ramped, we got to volume, and we're at scale. And a lot of challenges went in there because those 100 gig ports, which was 4 by 25 gigabit per second lanes, they were very cost effective, very power effective, and we'd really wrung that technology out. And really trying to get the 400 gig ports to match 4 times the 100 gig ports at price and at power was super challenging. So we had to go through, again, the iterations of the PAM4 signaling and trying to get the reliability and performance up to where it had to go. But it was super challenging. So at that same time as we were getting to scale, at the 2020 timeframe, we were starting to introduce 100 gig single lane rate SerDes into the market, again, to jettison what is now the 800 gig port deployments. But again, super challenging and getting to that lane rate, getting to that performance, across these tough channels. But what it allowed, I think, for an industry is people thought, okay, 50 gigs done, single lane rate. But at least Credo, I can talk from our perspective, we had flagship products in 28 nanometer at the time that were hitting all of those key metrics. But in our innovation curve, which always happens as you're moving to that next generation and trying to hit the challenges of the new frequency and the new channel loss, we innovated again, and we took the opportunity, again, because of the demands of the data center on lower power and higher scale, we moved to 12 nanometer in that innovation, and we're able to cut our power in half on the 50 gig lane rate. So therefore, all those retimers, all those DSPs that go into optical modules, all of those retimers that go into our AEC products, just allowed it to then go to that next generation so that data centers could really move. And that was a key point. If I go back to Alan's statement about the AECs, the reason why the AECs are there is at first, when the 400 gig ports were being connected, you could do the DAC in a limited environment, in a limited, kind of, chassis environment. But when you try to go to a massive, 50,000 server and higher deployment, if you looked at the airflow, the volume of cable, the weight associated with it, the DACs just didn't go to scale. So in order for the data centers to really embrace the 400 gig ports, they needed a technology. And the AECs allowed you to do, it's an active technology, but if you got the power to the right level of energy efficiency for that data center, then they could deploy, at scale, because it allowed them to, again, get the performance that they needed without the error insertion. And then it allowed them to, hit all the other parameters that you couldn't get there with the DAC. So if I fast forward and say, where are we now on the 800 gig, I'd say we're kind of where we were in 2017, 2018. We're ready and we're ramping. But again, in order to get to scale, we're going to all have to, at the chassis level, at the silicon level, at the call it the optics connection level and the AEC connection level, have all those systems fully tested and vetted for the hyperscale data centers, as Alan pointed out, to hit their massive millions of port deployments. And that's where we are today. And I think what we'll see, I didn't touch it on in this slide, but 200 gig SerDes are being developed, being tested. And what that's allowing us to go do to show that we can get to that next generation of, a new version of a 1.6 terabit port, or even beyond a 3.2 terabit, what really drops out of that is innovation that will allow the industry to turn the power even down further on the 100 gig lane rate, and therefore have another, called a midlife kicker on the 800 gig ports that again will allow that scale to continue through 2027 and 2028 that Alan mentioned. So again, super important, and I always say we're always tip of the spear, companies like Credo trying to say, okay, where are we going next? At what process node? How do we get to 224? How do we get to 448 lane rate? But right now, if you look at where the economics of the industry are and the demands of the data center from a user perspective, it's 800 gig ports from our view, for the next 5 to 6 years, clearly.
Okay, great, Jeff. Thank you. Alan, anything to add there? Charles, anything you guys want to add in, or should we move on?
Well, there's one very interesting point here that we'll touch on briefly, is in the effort to reduce cost. And this is the cost for the cloud operators, for example, or the network data center operators. They have to find different ways to reduce the cost. So while us individual, test system or a network switch manufacturer, or, Jeff's building silicon, he's also building active electrical cables. In the process of reducing cost, but increasing speeds and capabilities in the same volumetric space with the same or less amount of power, we've also have innovations that are highly complicated, like innovations in coherent optics, which connect data centers together. They call them campus connections, one building to another, or a whole collection of buildings to another collection of buildings. And with the innovations in coherent optics, which is a whole separate conversation, but just to touch on that, these are highly complex optics that the cloud service providers are, I believe, the greatest consumer of right now. And these address other types of cost reductions by removing certain types of, let's call it, traditional networking equipment, and having direct connections from an edge router to another edge router, and no other equipment in between, for example. So they're very expensive, but yet they remove very expensive pieces of equipment that used to be used in those connections. So we have other complicated aspects going on as well, and every aspect of what Jeff talked about all do have to be tested as well. So we have different. That's what I was saying. We have different axes going on here, not only in business challenges, but in technology challenges.
Yeah. And again, you bring up another great point there, Charles, on, having technologies in the coherent optics space that are eliminating what used to be, chassis of equipment. So again, it's another driving force down on kind of the energy efficiency that's being demanded, of the data center infrastructure overall.
Yeah. And an important point there is that with the advent of innovations in coherent optics, the semiconductor devices that help to drive those optics, they had to go to 5 nanometer technology to make those optics cost effective, power effective, and also to get enough features. There's a lot of features in these. And so the DSPs had to use 5 nanometer technology just to get to build those coherent optics. And now we have to take all this very high complexity and go from making 50,000 of these a year to several 100,000 of these a year or more right now. So that's another aspect. And Alan, I hope I didn't cut you off there.
Oh, no problem. I just wanted to give kind of you and Jeff some credit there too on something you didn't mention, which is when we were doing 100 gig, we were doing 4 lanes of 25. 400 doubled the lane count, right? So we did 8 of 50. 800 is 8 by 100, and 1.6T is probably going to be 16 by 100 as one of the form factors. So that's one of the ways like silicon is becoming more complex, but in an overall solution is reducing power and cost there. So that's an important complexity that the market has been achieving as we move to higher speeds as well.
All right, let's move on. Let's talk about some real world challenges for network operators that are implementing this new equipment and technology. So, once the networking equipment is developed, but prior to deployment into the network infrastructure, there are obviously many tests required of ultra high-speed Ethernet equipment to know that it does in fact meet published specs. So, Charles, maybe you can speak to it from the perspective of Keysight, and Jeff, maybe you can speak to it as a user of test equipment. If you could talk a little bit about these trends.
Sure, be happy to. So if we tried to describe the test plan, if you will, for a switch or a router, or even an optical transceiver or an active electrical cable, we could have an entire webinar just on the test plan. So that's how complicated it is, and they are very large. It's not unusual to run 100,000, 200,000, 300,000 tests on a device to qualify it over many months of effort by numerous test engineers with different skills. So knowing that, right, and knowing how difficult it is, what I'm trying to do here is to summarize what is really the top challenge. Well, the top challenge is to characterize the performance of a network device prior to deployment in a production network. If you think about it, I want to be sure if I'm Amazon and I'm going to change over my network infrastructure. It's been in place for 3 or 4 or 5 years on 100 gig E, in the last few years on 400 gig, and now I want to implement 800 gig E. I want to be absolutely sure that that equipment, when I put it in there, it works. It meets the specs that were advertised. It performs to the bandwidth and throughput and quality requirements that I have in my facility, right? And I want to turn that over to the network operating groups and say, this equipment is qualified. This optical transceiver is qualified. This active electrical cable is qualified. Well, this happens to involve a number of things. So we want to qualify the network and equipment. And when it comes to servers, we have to qualify the NICs, which are the front panel interface cards that go into the server to access those very powerful CPUs and gigantic amounts of memory. And then we have to make sure that servers with NICs, routers, and switches can all talk together, and that the optical transceivers and active electrical cables that connect them all, that they all work properly amongst all the different vendors. So we call that multi-vendor interoperability. Extremely important, because we have many different manufacturers of chips, different manufacturers of transceivers, different manufacturers of passive and active copper cables, different manufacturers of switches and routers and servers, and they're using different chips and different designs and different Ethernet speeds. And we have to take a look at all of that and make sure that they work together. And to do that, we need an independent source of truth, which typically is the measurement system. And then we have complicated problems, like, for example, when we connect a copper cable, which, by the way, at 100 gig used to be 5 meters long. At 400 gig, it shrunk down to 2.5 or 3 meters. And at 800 gig, we can't get a passive copper cable longer than 2 meters to work very well at the quality reliability requirements, which means active electrical cables become more and more important as the lane speeds get faster. So when we go from 400 gig to 800 gig, there's still 3 meter, 4 meter, and 5 meter applications for cables. We still have to figure out how to get there. We can't use the traditional passive copper direct attached cable. We have to now use enhanced cables that have the active electrical capabilities, retiming capabilities that Jeff's company builds. We need those.
And Charles, just to add on to that, and I mentioned you can do anything in a lab to some degree. And yet we can make, kind of short range, maybe 2 meter cables work at 100 gigabits per second, single lane rate technology. But the problem is what the industry is seeing is that's an extremely high gauge. It almost looks like a garden hose that you go through there. So if you look at the volume of that cable, the weight of that cable. So yeah, we can show the signal integrity in the test environment. But again, when you go to scale, when you're trying to put 32 switches or you're trying to rack NIC to TOR, in a complicated environment, we have airflow, you have weight, volume of cable, again, serviceability of the switches, serviceability of the NICs. You just can't get there. With an AEC, it really looks like a Cat 5, kind of connection. So you can bend them, you can move them, you can make the connections all over. So that's where we kind of play between, how do we test, but then how do we test for scale? And that's where the AECs really come in.
That's absolutely right. And I'll make another comment, which could lead to a longer conversation where we won't get into today, but important point. If I'm the network operator, let's say I'm Amazon or Google, right? And I have to think about how am I going to deploy 50,000 switches, right? And how am I going to test all of that? When I think about that, I know that I have to do some type of transition. So I can't just run in and throw 800 gig equipment into the network, into the production network. We just can't do that. There are many cases where we transition out a whole rack of or a cell of equipment, which is multiple racks. We might transition a cell out and put a new one in. Well, that means that some of those ports in the new cell might have to run at different lower speeds, what we call legacy speeds. They may have to run all the way down to 10 gig E in order to fit in the network infrastructure that's being replaced with newer, faster things, but you may have to connect legacy pieces together at the same time. So this means that slower speeds from 10 gig E and all the speeds in between to 800 gig E have to also be tested And they have different signaling, as we mentioned before, PAM4 and the traditional non-return to zero NRZ signaling. And when you have to do that, the complexity again increases, as we mentioned earlier, and it's tougher. So it's important to have test systems that can handle all these different speeds, as well as interconnects that can handle different speeds. So Jeff's company, for example, builds all different kinds of active electrical cables that can operate at different speeds, which is extremely important when we think about the massive scale required to change out to new equipment from existing.
Okay. Dynamite. Yeah, I was just going to say, we're starting to get tight on time. I want to make sure we have enough time for Q&A at the end. So Charles, if you could take us through a little bit about how Keysight's 400 and 800 gig test solutions are helping manufacturers of high-speed Ethernet network equipment and final end users of the equipment determine their readiness for production network.
Well, thank you, David. Yes, very quickly, as we are looking at our time element, what we really have to test is something called bit error ratio, bit error rates, and forward error correction performance under new tolerances. And I just listed a few of them that we would have to meet when we're doing our device qualification. And this means not only does the interconnect have to meet this, but the network switch or router or server has to meet these numbers and do actually far, far better, as we talked about. And we'll get to that. The other aspect is to be able to test 800 gig E related speeds over 106 lanes, 400 gig speeds on 53 gig lanes, and 100 gig speeds on 25 gig lanes. All of that, which we call multi-rate Ethernet, that has to be looked at as well. We have brand new optics and brand new active electrical cables that have to be tested that run these faster at 106 gig lane speeds. And then we have different types of chips, silicon that's used in different applications for shorter reach cables versus longer reach cables. And maybe Jeff, you could talk a little bit about short and long host chip to module applications for the silicon.
Yeah, I mean, there's like I said, everything's about, kind of power efficiency, picojoules per bit, whatever measure you really want to take on. Again, it's all about energy efficiency. So, how we look at that front panel, depending on the lane rate, again, single lane rate is how we think of things as a semiconductor, but that drives into your ports. So like the 400 gig port connectivity at 50 gig lane rate, we want to be able to see that get to the front panel and then get retimed, whether that's a pluggable optical module that gives you the longer reach, or the in-rack and rack-to-rack, which you can do with an AEC at dramatically lower power and dramatically lower pricing.
Right. And then think about interoperability, as I mentioned before. Right now, there's 11 major Ethernet speeds that have to be tested in the process of transitioning from 100 gig E to 400 gig E to an 800 gig E network infrastructure over 11 different speeds and many configurations of those speeds. So it gets complicated very quickly.
I was going to say, you throw in the auto negotiation, link training,
right.
You throw in the different CMIS, kind of standards you have to support to be able to handle all those. It's very complicated.
Yes, exactly. And then all in all, it boils down to, once we connect everything together, once we know that all these different manufacturers of equipment can talk to each other, now we have to standardize and do what we call benchmark testing. Does it really do 100% 800 gig E line rate at every frame packet size, using various protocols over many, many ports connected together? Or what is the actual performance? And what should my forward error correction performance be, so that I can put this device in my network and have some idea of its long-term reliability? So it means we have to do long duration testing and other things of that nature. So performance benchmarking, which we're just getting there now with 800 gig, it's just coming to light that performance benchmarking will have to be done in 2024, quite a bit of it. That's the next challenge that we're going to be facing. So with that, we'll move on a little bit more. And what I was talking about with forward error correction is we have a measurement, which I don't want to get too deep here. However, we want to count the number of symbol errors. Let's just call them bit errors that are occurred that occur in the forward error correction mechanism, which is a correction of the transmission while it happens, okay, on these high-speed lanes. And we want to be able to achieve where it says FEC margin in green. We want to know what's the maximum number of symbol errors I get in my forward error correction performance of the device, and can I get one that has less symbol errors? So if we're doing something with less than 6 symbol errors or less than 7, most of the time that's going to be a good device. If we get into an area where, well, I've got my device getting 9 or 10 or 11 symbol errors, even 8 in some cases, that might not be a device I want to put in my network for long-term super high reliability. So it becomes important to characterize the distribution of the measurements and what is the maximum error that we're seeing in a long duration test, which could be a 5-day long test, for example. So there's just a little bit about what we call the FEC margin and how to make that measurement. Another 2 important measurements is something called the frame loss ratio. You'll see in the red box, there's on the row that says FEC frame loss ratio, it says a bunch of zeros there. This is a new measurement for Ethernet. It's an old measurement actually from very long ago in the modem days, but it was resurrected. It's a phoenix. And it rises out of the ashes, and here it is again. And this means that if we have no packet loss, we have a frame loss ratio of 0. If we have no uncorrectable forward error correction symbol errors, in other words, if we have symbol errors that are less than the maximum to make it less than the maximum number of errors to actually corrupt the forward error correction mechanism and to actually lose packets, which when we lose what they call a FEC code word, we lose many packets at once. We don't just lose one packet like the old days. You lose many packets and you get an interruption in the service. We have to keep this number to 0. And in order to keep this number to 0, we need to keep the prefect bit error ratios in the to the minus 8s, 9s, 10s, 11s, 12s, 13s, even 14s, in order to know that my bit error ratio is so low, meaning so few bits, that even if I run this over a long period of time, over different temperatures and over different stresses of loads, and as the equipment heats up and the data center changes its environmental characteristics like temperature, humidity, I know that that device will make it. It will handle those stress changes. So we've got to do these tests, and we have to figure out how good our forward error correction is actually working. Now, when we go to make all of these measurements, what we want to be able to say is, well, okay, Keysight is offering these complicated, very expensive test equipment for 800 gigi and 400 gigi and 100 gigi speeds, and you can do all 11 speeds on one platform from 10 gig to 100 gigi. What do I get out of this? How do I spend $500,000 or $250,000? What do I get for this? Well, basically, by having a test tool that can do from 10 gig to 800 gigi, we really can simplify our regression test bed and our test automation, which, by the way, it's not the equipment costs where we have the highest cost. Where we have the highest cost in testing is many engineers working on gigantic test beds. Remember I mentioned hundreds of thousands of tests? This could be in the form of 500,000 to 1 million tests. And if that's true, and often it is, then you want to find ways to simplify that test bed and to simplify the test automation. So the more speeds we can do on our test system on a single port, we don't have to change our cables. We don't have to change our optics as much. We don't have to change a number of things. We can do an awful lot of what they call regression testing, so that I know that when I'm developing the equipment, or if I'm doing pre-deployment testing, if I buy the equipment and do that testing, I know that if I make a change, I can test it very quickly. I can get it done in a shorter period of time. The other aspect is we have to know the contribution of error of our silicon. What is the error it brings into the system that I talked about earlier? What's the error of that copper cable or that active electrical cable? What's the error of that optical transceiver? What's the error when it's connecting 2 switches together? What's the error when it connects hundreds of ports together, right? It's very good to know what that error budget is made up of. And so our test systems will help us to qualify the silicon, the copper cable, the active electrical cable, the optical transceiver, the switch, the router, the NIC, the server. We can characterize those things so you have some idea of what the error is before you deploy it. And then the other thing is, when we buy, we don't want to just buy. If you're a Google or a Microsoft or even Keysight, we don't buy from just one vendor. We buy from multiple vendors. And when we do that, we want to make sure not only do they work together, but that it's being cost effective, right? You get cost effectiveness doing that. And also, I want to be able to test those in a consistent and comparable way that I can rely on. So the test equipment becomes very important to know, well, I have manufacturer ABC supplying me 800 gig E switches with 32 or 64 ports of 800 gig on them. How do I know, if I deploy ABC anywhere in my network infrastructure around the globe, that it's going to work the way I think or has to work, right? So this is why you need a common denominator, which is usually the test system, and to help benchmark those performances and be able to compare them consistently over time. We might have to test these equipments over a year's period of time. So you really need to have and plan in advance to have this equipment in place. I don't know, Jeff or Alan, if you have any comments to that.
No, like I say, we, as a semiconductor, consumer of the Aries One and other boxes from Keysight, critical. Again, we deploy DSPs that go into optical modules. They need to be tested. We got our line card, which again are retimers, they're bit muxes, they're gearboxes. When we start talking about going from 56 down to 26, super critical for us to get out there. The auto negotiation and link training is super critical. So for us to be able to deploy to our customers they can do their system level testing, it's paramount.
Yeah, absolutely. Okay, and to top it all off, here's an actual picture of the Aries One 800 gig. We call it the -M because it's for multi-rate Ethernet. So we put a little reminder in there of how important it is to be able to test both PAM4 signaling and the Ethernet speeds based around that signaling and the traditional NRZ-based Ethernet speeds all in a single platform. And to be able to validate our bit error ratio and our forward error correction performance to qualify the link stability. How well do we stay connected to our network devices? And can we benchmark the throughput, that bandwidth growth we talked about? We're going to put equipment in there that addresses those growth requirements. We have to know that that equipment is 100% non-blocking throughput at every speed that I want to use that equipment for. So that becomes very important. And the idea is that from that, we then put our protocols, which runs above the data plane traffic. This runs at the next layer, at layer 3. And when we put our benchmark, our protocols, how we manage the networks, how we get all the devices to talk in what we call routing and intranetwork and networking routing protocols. How well does it work when we're running full blast traffic with thousands of subscribers per port? How well does that service work? How well does it go together? And with Aries One 800 gig system, you can do that. You can test everything from 10 gig E to 800 gig E and all 11 speeds in between. And we can also do the networking protocols on top of that, which becomes very important to do what they call system testing. So we know how do the devices, the routers and switches and servers work in the actual system that I plan to deploy with the protocols that makes those devices talk together. So basically, we think that Aries 1M is the first to market with all of these speeds and all of the protocols that are supported to be able to test from layer 1 to layer 3 in a comprehensive test platform. And we believe that's the first one available to do that.
Okay, fabulous. That's great. Let's take some questions. We've got a bunch of them that came in from the audience. And I think actually, Charles, let's stay with you. I think this first one would go for you, but Jeff, and Alan, feel free to chime in. So Charles, you had discussed at some length the challenges of deploying 800 gig capable devices and testing PAM4 signaling on those devices. So in your opinion, what are the most difficult to test and how can they be made easier?
Yeah, the most difficult to test is, I think, if once we get out of what we'll call physical layer 1 testing, in other words, testing the signals at the silicon level, that is very difficult testing. And Jeff is probably going to bob his head up and down because I know that there's a lot of investment by every company to test silicon. But once we leave the silicon and get into what we call a system could be an active electrical cable. That's a system. An optical transceiver. That is a little system, but it's a system. When those then get connected to switches, which are very complex, large systems, or a router even more complex and larger, when we get into those systems, really what we have to do now at the very base level is the forward error correction performance. We really need to know, if I run that test for 5 days, will my FEC errors grow and grow and grow on me over those 5 days and eventually get an errored FEC code word? And if I get one of those errored FEC code words, I'm going to drop packets. I'm going to drop packets. My end user experience is going to be affected. Where is that boundary? What is that FEC margin? I think that's the number one measurement that we have to make at what I'll call the system level in order to qualify our networking component or device.
Yeah, I couldn't agree more, Charles. I mean, at our level, yeah, we are the rubber hits the road with the SerDes technology. So that's ultimately critical. And as a Credo company, we do license our technology. So that satisfies the bigger chips and they have to go to the higher levels. But even the humble chips that we build, again, DSPs that go in those optical subsystems, as you mentioned, our retimers that go into our AECs as a system and a cable, or just on big chassis that are switches and router chassis that are in the market. We're responsible for that. We also do MACsec security and IPsec security. So being able to go up the protocol stack and go beyond just the layer 1 and test our devices is just a fundamental step to get, again, to the chassis, to get to the rack level deployments that the data center needs. So again, paramount that we get it right. And like I say, the Aries one has been a good choice for us from the 400 gig generation now to the 800 gig generation.
Great.
Okay, cool. Let's take a couple more questions. And Jeff, I think this one would be for you, and it's about deploying 800 gig ports at scale. This references one of the slides that was shown in the presentation. So a question is, to deploy 800 gig ports at scale, are all the verification and validation mechanisms in place at 100 gig per lane throughout to support the ramp highlighted in the presentation, do you think?
Yes, absolutely. Like I say, I think we've been as an industry, with 100 gig lane rate, going back to 2018 timeframe. So getting the bit error rates, I guess, at different channel loss profiles has been in place. But again, a lot of the work at the protocol level, at the system level, and again, going back to this, I talk energy efficiency a lot, when I'm out in the open market. But it really, where we were 4 years ago with readiness, we just weren't there from, a test ecosystem. We weren't there from a power management perspective on how we manage the ports. Again, we got to get at the right performance, but it's got to be at a lower power relative and a picojoule per bit perspective, and it's got to have the economics in play. Again, that was that big delay between 100 gig ports to 400 gig ports, primarily based on power and economics. And again, being able to build at that scale with all the different components at the lasers for the optics. So I think we've done a good job as an industry, as we mentioned earlier, and Alan said it, we have to be accelerating to this next generation and then going from 400 gig ports, again, 56 gig signaling, to the 100 gig ports, which is, 112 gig signaling, is here and ready to deploy. Are we ready for the 224 gig signaling? I don't believe we're there yet. I think when we go to the 1.6 terabit ports, that will be 16, by 100 as its first and most scalable deployment. But again, I think the industry on the back of 112 gig SerDes technology is ready to go.
Okay, cool. So I've got one follow-up question to that, Jeff, and then one more for Alan, and then we'll be out of time. So the follow-up to that one, Jeff, is are the current process technology nodes sufficient to meet the price, performance, and power metrics for the 800 gig rollout?
Yes, I believe we're there. I mean, depending on what you're building as a chip, I mean, the challenges of building, a 50 terabit or 100 terabit switch are different than building a 2 by 800 gig port retimer or gearbox or MACsec device. But yeah, I think we're there, at the process nodes scaling anywhere between the new 3 nanometer and the 5 nanometer range for the bigger chips. Just to give the audience some color, at Credo, we're still at the 16 nanometer node for our 100 gig signaling, so our 800 gig technology, and we're hitting the power, price, and performance requirements. So we have a lot of room to go down, and I think others in the industry that would be cooperative or competitive to us are in a similar. They might be one process node more aggressive because they have to, but we've got headroom at Credo to take it down to 5 for lower power and take it down to 3 for even lower power.
Okay, great. All right, Alan, we're going to give you the last word. It is a question about AI. Where would we be without at least one question on AI? So the question is, how are AI applications changing the design of network infrastructure, and what is different versus the design of traditional data center infrastructure, do you think?
Yeah, so I think AI is the most significant change in infrastructure we've had since the cloud launched, or say 15 to 20 years ago. It completely changes how you build everything out. The most notable change that we're seeing from a supplier point of view there is fundamentally AI has multiple networks. So we can call it a front end and back end network, or your traditional network, and then an AI fabric. So you have more than one network. And each network has different performance characteristics. Like if you drop a packet on your backend or fabric network, your AI performance can have just on one packet being dropped. And that's very different than, say, an email server or a web front end that we face on a daily basis there. So it's this concept of multiple fabrics or networks versus one, and different performance characteristics out there. And then the scale, again, like we saw when the cloud first started. So that's kind of my view from a market level. I don't know, Jeff, if you want to chime in there on what you're seeing, like with customers as they're playing around.
Yeah, it's absolutely, again, whether you call it primary or secondary, it's an additive networking infrastructure play. And the most important part is it's going right after the highest speed ports. We're seeing a match between, what the server kind of NIC requirements are, 800 gig ports deployment to match the networking speeds. So that's I think it's new, it's growing the fastest, and it's requiring the high speed connection. So it'll outstrip the traditional networks, in the years to come.
Okay, fabulous. Thank you very much, guys, for being here today. We are out of time. Many thanks to Charles Seifert with Keysight Technologies, Jeff Twombly with the Credo Technology Group, Alan Weckel with the 650 Group. Many thanks to Keysight for sponsoring this event, and to VIB. I'm Dave Littman at Truth in IT. Thanks so much for coming, everyone, today. We want to wish you all a great day ahead.